things about it. The number of bedrooms, the number of bathrooms, and the number of garages that it has. And we might have a whole bunch of other houses that are nearby, and we know what their sale prices are. What might we do with that? So we know these, okay. If we come back to our definition of a regression problem here, we're trying to figure out the relationships between a dependent variable, often called the outcome variable, and one or more independent variables, often called predictors, covariates, or features. Okay. So in our case, our independent variables might be the number of bedrooms, 4, the number of bathrooms, 2, and the number of garages, 2 as well. So for our machine learning model or deep learning algorithm, we're going to have to encode these in some numerical way because we can't just pass 4 bedrooms, 2 bathrooms, 2 car spots. So we'll put them into a numerical encoding, and as you might see here, this is a one-hot encoded. We've seen this before in the TensorFlow basics section. And so if we had this array here, or this tensor, this vector could be number of bedrooms. So it's 0, 0, 0, 1. Now what that would mean is that, does it have 1 bedroom? No. Does it have 2 bedroom? No. Does it have 3 bedrooms? No. Does it have 4? Yes. So we put a 1 there. And in this case, does it have 1 bathroom? No. Does it have 2 bathrooms? Yes. Does it have 1 garage? Yes. So 0 in case of one hot encoding encodes for not that thing, and 1 encodes for that thing. So that might be our numerical encoding. Wonderful. We put these into here, and that's our inputs to our machine learning model. And these are often called input features, or in Wikipedia terms, predictors, covariates, or features. So features is probably the most dominant term that I use in practice and we're going to use throughout this course. If you ever hear input features, it's some kind of information about the data we're using that goes into our machine learning algorithm. And so in our case, if we want to put our inputs into a machine learning algorithm, so often one, and you'll find this in deep learning a lot, is that often an algorithm for your problem already exists. So that means someone has built something that has worked before for their problem, might be very similar to your problem, and you can utilize that for whatever you're working on. However, if it doesn't already exist, we can see how we can build our own. That's what we're going to be practicing. We'll see how we can build our own. But later on in the course, we're going to see how we can use algorithms that already exist. And finally, if we have a look at what our outputs might be, we might, if we're trying to predict the sale price of this house here, based on the fact that it has 4 bedrooms, 2 bathrooms, 2 car spots, and it's on a pretty big piece of land, if we wanted to make an offer, we're using our algorithm to figure out how much we should offer at auction. Our algorithm's telling us we should offer $939,700. Now, where does it get this predicted output from? If we have a look at what it actually would sell for, $940,000. So we weren't too far off here. We'll figure out some evaluation metrics to compare predicted outputs of our deep learning models to the actual outputs of what they should be, for regression problems, that is. Now, this predicted output comes from looking at lots of these actual outputs. So remember how we talked about supervised learning? Well, this is an example of supervised learning. So we might have 100 or 1,000 or tens of thousands of different homes with all of their input features and their actual sale price. And then we might feed these inputs and outputs to our machine learning algorithm, and it's going to learn the relationships. Remember, we come back to our definition of a regression problem. Regression analysis is a set of statistical processes for estimating the relationships between a dependent variable, right, so our sale prices, and one or more independent variables, so our input features here. So after our machine learning algorithm has looked at many, many examples, comes from looking at lots of these, of input features and outputs of house sale prices, it's going to learn the relationships between the input features and the outputs here. And then for use cases where we would like to predict the potential output of a home that we don't know the actual sale price for, we can feed its input features into our algorithm and have a suggested output of what the sale price or what we should pay if we were going to auction. So this is just an example of what regression inputs and outputs look like. We're going to have some practice writing code to do this very shortly. So another big point is once we've defined our inputs and outputs, and I can't emphasize this enough, is this is what we'll be focused on a lot of the time in machine learning and deep learning, is the blue parts here, defining our inputs, defining our outputs. And now another key term is when we're talking about inputs and outputs, is input and output shapes. So say here, we were taking our input features, numerically encoding them, feeding them to our machine learning model as inputs. Our machine learning algorithm works out the patterns or utilizes its already learned patterns to produce an output, aka the sale price of our home. What might be the shape of our inputs? Because remember, our numerical encoding is going to be in the form of a tensor. And this output here doesn't look like it, but it will also be in the form of a tensor. So here we go here. We've got bedroom, bathroom, garage represented as a tensor. And in this case, the shape is going to be 3 because we've got 3 input vectors here. Now, don't be confused by this outer bracket here. Because we've got 3 input features, the shape of our input layer to our machine learning model is going to be 3. 1 for bedroom, 1 for bathroom, and 1 for garage. We'll represent this as a tensor. And for our outputs in our regression problem, in this case, can you guess the shape? Is going to be 1. So in our case, for each example that we're going to pass through our machine learning algorithm, each sample will have an input shape of 3. So we need number of bedrooms, number of bathrooms, number of garages. And each sample will have an output shape of 1 for the price of what we're trying to predict. And now this is just for our housing price prediction example. We can adjust these. So here, the bedroom, bathroom, garage, to be almost as many different inputs as we want. But usually for a regression problem, the output shape is often 1 because we're trying to predict some sort of number. So again, if we come back to Wikipedia terms, we're trying to figure out the relationships between a dependent variable, often called the outcome variable, and one or more independent variables. So in our case, these are our independent variables, and this is our outcome variable, or our dependent variable. Now, with that being said, we've covered inputs and outputs of our regression problem. Let's now have a look at what that might look like in terms of building or writing neural network code. We'll have a look at it in the concept of an architecture of a neural network regression model. Recall in a previous section that we covered the anatomy of neural networks. So essentially every neural network that you build will have an input layer, some number of hidden layers, and an output layer. And for your input layer, this is where your data goes in. Now, hidden layers is plural on purpose or optional plural. It can have 1 up to 100. Some neural networks even have 1,000 hidden layers. It really depends on what problem you're working on. And now that's where the deep and deep learning comes from. So if you imagine if we had 10 of these hidden layers laid out here, or the more we had, the deeper our deep neural network would be. And then for the output layer, this is where the outputs or the learned representation or prediction probabilities of your neural network come. And within the hidden layers is often where your neural network is learning patterns or weights in the data. And so keeping this in mind, if we have an input layer, a hidden layer, and an output layer, what might the architecture of a neural network regression algorithm look like if we wanted to build one with TensorFlow? So this is what the typical architecture of a regression model in TensorFlow will look like. So in our case, we have a few hyperparameters here. Remember, a hyperparameter is a setting that you as a data analyst or a machine learning engineer can change. So we might have the input layer shape, the hidden layers, the neurons per hidden layer, output layer shape, hidden activation. We haven't covered that yet. The output activation, the loss function, and the optimizer. Now we haven't covered the bottom half of this little graph here, but that's okay. We're going to get very familiar with that as we write code. And now I just want to emphasize that I've adapted this from page 293 of the Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow, book by Aurélien Guérin, which is a phenomenal book. This is probably going to be my #1 external resource to go along with this course. is this book. I've read it end to end in its entirety, and I'd highly recommend it if you're looking at learning more with TensorFlow. But that's beside the point. We're getting hands-on here. Now, in terms of the typical value for each of these, the input layer shape, we've covered this a little bit before. So if we were trying to predict the sale prices of different houses, we might have an input layer shape as the same as the number of input features that we have. E.g. would be 3 for number of bedrooms, bathrooms, and car spaces in housing price prediction. Hidden layers, the value you have here is very problem specific. The minimum is 1, the maximum is unlimited. Again, the neurons per hidden layer is going to be problem specific again. So if we come back to our anatomy of neural networks, so this has 3 hidden neurons. So not only can you customize how many of these layers that you have, you can customize how many of these little circles here, also referred to as neurons. So you could have 100 neurons here times 100 layers, and that would be a very deep model. Now, the output layer shape, this is the same for the desired prediction shape. For example, 1 for our housing price prediction problem. Hidden activation is usually ReLU, which is rectified linear unit. Output activation, this is going to be problem specific, but these are some typical values here. The loss function for a regression model is, the default one is usually mean squared error or mean absolute error / Huber loss, so which is a combination of mean absolute and mean squared error if you have outliers in your data. Again, we haven't covered these 4 here. We're going to see what they mean shortly. And then the optimizer, which is a way of how our neural network improves its predictions, is usually going to be stochastic. Oh, that's a fun word to say. Stochastic gradient descent. Stochastic is a fancy word for random. Or the atom optimizer, which is a very good default value. So let's have a look here what this looks like in TensorFlow code. We haven't written any of this, so don't worry if it feels foreign to you. We're going to write a lot of this going forward, but I just want to relate the architecture of a regression model, see what we're going to start working towards. By the end of this module that we're covering, this section, you're going to be able to write these yourself. So let's have a look. This is the input layer. So the input layer is in the blue. So we see the shape is defined here as 3 because we're working with our housing price prediction. The hidden layers is in this other little blue shade here. So these are known as hidden layers. So we've got an input here and then an output here. Remember, all neural networks have some sort of input, some sort of output. Then the hidden layers, in our case, we have 1, 2, 3. And if we look for the neurons per hidden layer, is often this first number. So we have it in green. In our case, we've got 100 neurons in the first hidden layer. We've got 100 neurons in the second hidden layer. And again, the same for the third hidden layer. Now our output layer shape, we can see here in the yellow. This is the same shape as our desired prediction shape. In our case, this would be a great output shape for our housing price prediction. Then we have the hidden activation parameter. In our case, it's the ReLU, which is a rectified linear unit. So that we can set that using the activation parameter. And then for our output activation, which is just simply the output activation function for our output layer, we've decided to set this one as none. And then for our loss function, if we come down here, we've got step 2, which is compiling a model. So this is step 1 is we created a model. Step 2 is we have to compile it in TensorFlow. Again, we're going to be writing a lot of this code going forward. So we define our loss function. This measures how wrong our neural network's predictions are. So when it's learning the relationships between our independent variables and our dependent variables, in other words, the number of bedrooms, bathrooms, and car spaces, and the sale prices of our homes, this loss function is going to measure how wrong our neural network's relationships are. And the optimizer here, in our case, we've set it to, which is in the black square here, we've set it to the atom optimizer, is going to inform our neural network how it should improve our patterns to reduce the loss function. So again, if we look at this in the context of our housing price prediction problem, we see we have the input features here, which is going to go into our input shape. They'll pass through the hidden layers, which will learn the patterns between the input features and the output variable. And then it's going to come out into our output layer, which is going to output something like this. And then the loss function is going to tell us, or tell our neural network, how wrong the relationships between these and this is. And then the optimizer will tell our neural network how to improve the patterns it's learning between the input variables and the output variable. And then here, the fit model is telling our model to look at a whole bunch of different examples in the training data for 100 laps of the data. So that's what the epochs variable stands for. Again, a lot of things we haven't covered here, but as I said, we're going to be writing a lot of code. And actually, I think it's about time we did that. So we've looked at some code here. We haven't written code, so we've gone against our rule. If in doubt, write the code. Let's see how we'll create some of this. And yeah, we'll create some data for regression problems. We'll write some code, and we'll get hands-on with neural network regression models. We've covered some of the fundamental principles of regression modeling with TensorFlow, specifically what is a regression problem. But now let's see how we might write some code to actually do that, or to actually work on our own regression problems. So I'm going to start a new web browser here. I'm going to come to colab.research.google.com. I'm going to create a new notebook. Now we'll wait for this to load up. Just going to zoom in here. There we go. Now I'm going to call mine O1 Neural Network Regression with TensorFlow. And I'm going to add the little video tag here. This is the notebook that I'm writing during the videos. If you want the ground truth notebook, so the notebook that I'm getting the information for this video off, remember you can go to the course GitHub, which is github.com/mrdberg/TensorFlow Deep Learning. This will be linked throughout the course. At the moment, while I'm recording this, it's still a work in progress. But if you come here to O1 Neural Network Regression in TensorFlow, you'll have all of the information we're working on in a very succinct manner. So there's a lot more annotations in this one. In the notebook that we work on during the course, this one here, we're going to be focused on writing code. So if you want all the commentary around it, check out the course GitHub, specifically the notebook without the video tag at the end. So I'll just close that. And here we go. So let's write our title in Markdown. So Introduction to Regression with Neural Networks in TensorFlow. Beautiful. I'm going to turn this into Markdown by pressing Command MM on my Mac. Might be Control MM if you're using Windows machine. So we're going to write here, there are many definitions for a regression problem, but in our case, we're going to simplify it. Predicting a numerical variable based on some other combination of variables. Even shorter, predicting a number. That's what we're going to do. We're going to be writing neural network code. Did I spell anything wrong here? Probably. Definitions is wrong. Predicting a number based on some other numbers. Nice and simple. Actually, that's probably a definition for neural networks in general. But this is what we're going to start with. And we had a lecture before that was what we're going to cover, so refer to that one. But let's just get started. We need to get hands-on by, first we're going to need some data. So how about we do that? What should we start with? Import TensorFlow. So we need to import TensorFlow as TF, and then we're going to check our TensorFlow version. So for this course, we need 2 point something, so 2 plus. And you'll notice here that we're not connected to a Colab instance just yet. But the beautiful thing is, as soon as we run a cell, it's going to automatically connect to a Colab instance. So we'll import TensorFlow here. Wonderful. 2.3.0. So this is the version that I'm on. If you're watching this at a later date, you might be on a later version. But as long as you're 2 point something, you should be right for this series of videos. Let's start off by creating some data to view and fit. So we had a look at what is a regression problem before, regression analysis, and it looked something like this. So we have the blue dots could be our data points, and our regression model is this red line through the middle. So that's the relationship that we're trying to learn, right? Between a dependent variable and one or more independent variables. So let's create some data that looks like this. How might we do that? Let's try NumPy as NP, and we'll also import matplotlib .pyplot as plt. So we need to create the features, which we'll call x. Again, nomenclature for features is generally called x in the form of a capital. So this is np array. We're going to just create this manually. Maybe we start from my favorite number, 7, or specifically -7, -4, -1. You might be able to work out the pattern of these numbers that I'm creating as well. That's what I want you to start thinking about, is that whenever you're viewing data, before you write a machine learning model or some sort of deep learning model to figure out patterns, see if you can understand them yourself. What's your gut feeling? So np array, we'll create our labels as well, which is typically defined by y in a lowercase. So we'll go here, 3.0, 6.0, 9.0. Now, if you were trying to figure out the relationship between x and y, what might you do? There we go. We've got x and y. Now, if we want to visualize it, remember one of our other mottos is visualize, visualize, visualize. We're going to see that a lot throughout the course. Boom. Plot.scatter. Okay. We've got a very simple line here. So you could think of x as our independent variables and y as our dependent variable. If we have a look at our regression analysis little diagram, ours looks something like that, but just this has got many more samples. We're starting nice and simple. So there we go. Now, what might we want to do that? So let's try work out the pattern between x and y just as it is. So x is -7 where y is 3. And then x is -4 where y is 6. And -1, 9, 2, and 12. Are you sensing a relationship here? How might we manipulate x to get y? Well, I'll tell you the rule I just figured out. Y equals x plus 10. Does this work? X plus 10. Do we get y? Beautiful. So if we want to go y equals x plus 10, true, 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 true. Beautiful. So the relationship we would try to get for our neural network to learn is this here. This is the relationship or the function between our x and y. In other words, our input features and our labels. In Wikipedia terms, our independent variable and our dependent variable. So let's have a look at what our input and output shapes. So if we were to build a model between x and y, what might be the input and output shapes of our model? If we come back to our keynote, remember we defined our input shapes for our housing prediction problem or housing pricing prediction problem. If we were to take in these independent variables, number of bedrooms, number of bathrooms, number of garages, so bedroom, bathroom, garage, the shape would be 3, and then the output shape would be 1. And remember, these will vary depending on the problem you're working on. So in our case, our problem, if we just want to predict this simple line here, it varies from the problem we're looking at here. So if we had 3 input variables for 1 output variable here, what might be the shapes of our input and output variables for this problem? Let's create a demo tensor for our housing price prediction problem. This is a very, very important point for all the neural networks that you build. So I want you to pay attention to this one. So the house info equals, let's create a tensor. Remember our input shapes to neural networks, often numerical tensors, but this one we'll just treat it as a string tensor for now. Garage. And now the house price is going to be TF constant 939,700 or something like that. And now let's check out house info and house price. Okay, there's our shape. Beautiful. So what we've done is we've just converted here this demo input and output shape into actual tensors. Wonderful. So the input shape is going to be 3 and the output shape is going to be 1 because we're using the house info to predict the house price. Now in our case, we want to use X to predict Y. So, let's have a think. What might be the input shape? So if we go input shape equals, maybe it's X dot shape, and the output shape equals Y dot shape. Let's check the input shape and the output shape. 8 and 8. Does that make sense? Because really we want to just know what the Y is based on this sample of X. And really we just want to know what the Y is here based on this sample of X. So what if it was just one sample? So if we did X0, we want to use X0 to predict Y0. So -7 to predict 3. And we also want to use X1 to predict Y1. Just like in our housing price demo, we want to use one house to predict the price of one house, or the input features of one house to predict the price of one house. Same for this sample problem. We want to use one input feature of X to predict one Y value. Same again here. So what if we check the shape of this? From this, it seems that our inputs and outputs have no shape. How could that be? I mean, it's because no matter what kind of data we pass to our model, it's going to take an input and return as output some kind of tensor. But in our case, because of our data set, it's only two small lists of numbers here. We're looking at a special kind of tensor. Do you remember when we went over the different types of tensors that you might come into? We're looking at scalars here. Specifically a rank 0, well, scalars is specifically a rank 0 tensor. So if we go x0.ndim, it has 0 dimensions. So that's why it has no shape. So let's take a look at the samples individually. So x0, y0. Wonderful. So in our case, we're trying to predict or build a model that's going to take as input -7 and produce as output 3.0. So this is where you're going to run into a whole bunch of input and output shape trouble, is when you get examples like this that don't really make sense. But how I want you to think about this is we're going to use one X value to predict one Y value. So keep that in mind. And in the next video, we'll see how we might create a model to do so. In the previous video, we created some sample data, so some sample input features, and some sample labels. And what we're trying to do is model the relationship between X and Y, in other words, the relationship between our features and labels. And we checked out our input and output shapes, which are kind of confusing, because when we checked out the shape of our, in our case, NumPy arrays, actually, let's turn these into tensors. How might we do that? Turn our NumPy arrays into tensors. So remember, from our TensorFlow fundamentals section, we can turn NumPy array or NumPy arrays into tensors by just passing them to TensorFlow.constant or tf.constant. And then if we wanted to check the x.shape, y.shape, we'll just print x and y actually. So there we go. Now our NumPy arrays are in the form of tensors. Beautiful. And we got a little confused when we checked the input and the output shape. So let's do it again while they're in tensor form. So input shape equals x0 dot shape and output shape equals y0 dot shape, input shape, output shape. And we got to get a little confused because they have no dimension here, because what we're doing is when it has no dimension, it's a scalar value. So it's a single value. But then we figured out by just investigating our data that we want to use one input value to predict one output value. So that's our input and output shapes there. Now, how might we build a model to do that? How might we, scatter x, y. How might we build a model to figure out the relationships here? Well, we haven't covered that, so if you don't know the answer to that, that's perfectly fine. But let's start with steps in modeling with TensorFlow. That's what we're going to cover here. So, the first one is number one, is creating a model. In here, you're going to define the input and output layers, as well as the hidden layers of a neural network. And if you're using deep learning, that is, of a deep learning model. Wonderful. Number two, we have to compile a model. We need to define the loss function. In other words, the function which tells our model how wrong it is, and the optimizer. The optimizer tells our model how to improve the patterns it's learning, and evaluation metrics. So what we can use to interpret the performance of our model. Beautiful. And then finally, 3 is fitting a model. So this is letting the model try to find patterns between X and Y, or features and labels. Beautiful. So we have 3 steps here. Now if we come into, we've got a beautiful diagram here, which is steps in modeling with TensorFlow. Whoa, look at that. A beautiful, colorful diagram. Step 1 is we have to get our data ready. So if we were working on an image classification problem to figure out what type of food is in an image, we'd have to turn it into tensors. But in our case, we already have our data in tensors because if we have a look, we've turned X and Y into tensors. So our data is already in tensors. Wonderful. Now, step 2, once our data is in tensors, we can build or pick a pre-trained model to suit our problem. We can use pure TensorFlow or TensorFlow Hub. We'll see that in a later video. So that would be step 1 here, would be creating a model specified to your problem. Wonderful. Then we fit the model to the data and make a prediction. So that would be down here, fitting the model. But actually, in TensorFlow, building or picking a pre-trained model often involves step 1 and 2 are very synergistic with each other, meaning if you do create a model or pick a pre-trained model, once you instantiate it, you basically always have to compile it. That tells TensorFlow that, hey, I've got this model instantiated, I've got it set up, now I'm compiling it, I'm telling you that I'm ready to use it. So then we go on to step 3, is to fit the model. Wonderful, model.fit, and we might fit it to the training data. We might let it look at the training data 5 times. And then we have number 4 is evaluate the model. So once the model has found patterns in the training data, we might evaluate our model on the testing data. And then if we keep going, we can improve via experimentation, and then we can save and reload our trained model. But let's go back here. Let's see how we might actually go through these 3 steps here. And what I'm going to do, I'm going to turn these into bold so they're just a little bit more pretty. Because that's what we're doing here. We're creating art. So what I might do is set the random seed so we have some reproducibility. tf.random set seed. 42. I'm going to use 42, which is if you're wondering why I'm using 42, it's the answer to the universe. I'll let you look that one up. And then we're going to go number 1. Create a model using the sequential API. You might be wondering what that means, but we'll get into that in a second. I'm going to write the code first. Model equals tf.keras.sequential and then we're going to open bracket, and then we have, so this is basically saying to TensorFlow, hey, I want to create a model, and I want you to sequentially go through the following. We're going to just make this with one layer. tf.keras.layers.dense. We're going to have 1. There we go. You might be wondering why I'm using 1, because in our case, what do we want to do? We want to build a model to take as input one number and predict one number. So that's why I have 1 here. We go down. We're going to go step number 2, compile the model. So model.compile equals loss equals tf keras dot losses dot mae. So in our case, we have loss. MAE is short for mean absolute error. So let's have a look. Remember, if you don't know something, mean absolute error. What is this? So in statistics, mean absolute error is a measure of errors between paired observations expressing the same phenomenon. What about, do we have images? Comparison of two observations where x1 equals 2, mean absolute error. This is what you're going to come across. You're going to come across a whole bunch of different explanations. But what the best thing to do is to just check them out and see if something catches your eye. So examples of y versus x include comparison of predicted versus observed. Comparisons of predicted versus observed. All right. Subsequent time versus initial time. And one technique of measurement versus an alternative technique of measurement. What if we looked up just the function that we wrote, tf keras losses.mae. Here we go. Computes the mean absolute error between labels and predictions. Wonderful. So y true, y pred. All right. And there's the function. So it's the mean of the absolute of y minus y pred. So I'm guessing that y prediction is the prediction our model makes, and y true is the actual value it should be. So we make it the absolute value here, so it's a positive number, and then we get the average from that. Okay, so mean absolute error is just saying there's the absolute, and there's the mean. So it's just saying, on average, how wrong are our predictions? Okay. That's a little bit easier than what it first looked like. Now the optimizer is, we're going to set it as tf keras optimizers.sgd. Now, SGD is short for stochastic gradient descent. Wonderful. Now, again, if you're not sure what SGD is, go, what is stochastic gradient descent? So I'll let you go through those in your own time of what stochastic gradient descent is. But just what you need to know for now is that an optimizer tells our neural network how it should improve. And then we'll go here, and we want metrics is, we're going to use MAE as well. Now, a lot of functions in TensorFlow, if they have a shortcut name, MAE or SGD, you can often use a string variable to define the fact that you want to use that specific function. So in this case, we could remove that and write SGD. But we're going to remove that. There we go. So that's our compile done. And now we're going to fit the model, which is model.fit. And we're going to fit it on X and Y for 5 laps. So this is what the fit function takes. So we create the model, we compile the model, and we fit the model, aka telling our model, look at X and Y and try and figure out the patterns. And you've got 5 opportunities of going through all of the X values and all of the Y values and trying to find those patterns or figure out the relationship. If we set this to 100, we'd say you have 100 opportunities of going through all of X and all of Y. But because we want to keep our experiments nice and short to begin with, we'll only set it to 5. All right. So before we run this, We did say that we use the sequential API. How do we find out what sequential means in TensorFlow? So if we wanted to find out what the docstring of this method here is, oh, there we go. Colab automatically opens it up. But in my case, I'm going to press Shift Command Space as it goes here. So sequential groups a linear stack of layers into a tf.keras.model. Sequential provides training and inference features on this model. All right. So we get an example of how we can create a sequential model. Now, in TensorFlow and Keras, there's two different types or two main types of creating models. We've used a sequential API here. So we can go TensorFlow, Keras. Now, this is if I already know what the difference is between the sequential and functional API is. That's a little reveal of what we're going to look into. But this is how I'd find out information about TF Keras sequential. I go here. Sequential groups a linear stack of layers into TF Keras model. Now there we go. tf.keras.sequential equals layers equals none. Here's a whole bunch of different guides I could go through to figure it out. I could go through some tutorials if I wanted to. And there's actually, the documentation is showing us a different way. So we could create, this is what I also do sometimes. I just copy the code sample. I come back to my notebook. I copy it here, and then below it, I'm going to write exactly what it writes out here. So model equals tf.keras.sequential. And then I do here model.add.keras.layers.dense 8 input shape. Now this gives me the feeling of writing this actual code. Input shape 16. And then so on, so on. Now, I want you to think about, if you've seen this example here, how might we convert our own example into this? So let's try. We'll go, we've got our sample here. We might go model equals tf keras, and again, looking at this one, dot sequential, wonderful. And then model.add, looking at this, we want to put this in there. Model.add tf.keras.layers.dense 1. So there we go. We've just got reproduced the exact same thing here. Now, the reason why I'm showing you this is because in TensorFlow, there are actually a fair few ways to do things. So this is with the sequential API. You can put your layers, you can use the .add method to add them to your sequential model, or you can put them into a list, as we've done here, and add them to your layer. So tf.keras.layers.dense.1 would be the same as adding that there. Does that make sense? If not, that's all right. Have a little bit of a play around, have a practice, check out we'll delete this cell here because we're going to use this methodology for the time being. Have a look at the TensorFlow documentation if you'd like to have a little bit more practice. Rewrite all of this code for yourself. But let's get back into here. We've set up our model here, steps in modeling. We've created a model, we've compiled the model, and it's time to fit our model. So you're ready to run your first neural network of this entire course? I hope you are. So let's try it out. 3, 2, 1. Oh, look at that. So we get a warning here. What does this say? Dense is casting an input tensor from D-type, from float 64 to the layers D-type of float 32, which is new behavior in TensorFlow 2. Okay, the layer has D-type float 32 because it defaults to float X. So we discussed this before of if you intended to run this layer in float 32, you can safely ignore this warning. If in doubt, this warning is likely only an issue if you are porting a TensorFlow 1.x model to TensorFlow 2. No, we're not doing that. To change all your layers to have D-type float 64 by default, we can set the back end to float 64. How might we just change our layer or our input data to D-type equals float? Because you see how we create it with NumPy? The default data type is float 64. So let's change the D-type to TF float 32. And same again, D-type equals TF float 32. with dtype float32? Not. Well, what if we go tf.cast, and then we go pass here, dtype equals float32, and then we'll do the same here, tf.cast, dtype equals float32. There we go. We'll change this with dtype float32. So now we have float32 tensors. What if we were to run this model again? Remember, this warning was telling us that the layer uses float32 by default, but originally our input, x and y, were float64. Let's run this again. Boom! Wonderful. So this goes very quickly. So you can see here, this is what the output is when you're going to fit a model, is it tells us this is lap 1 of the data, lap 2 of the data, lap 3, this is how long it took, and this is our loss function, so how wrong our machine learning, our deep neural network is when we're trying to predict x and y. So right now, on average, when our model uses an x value to predict y, it is wrong by 11.5, and then it slowly improves to be wrong by 10.9. And then because we've set our metrics to be the same as the loss function, we get the same output here. So this is loss, this is our evaluation metric. Now, if we wanted to use our machine learning model to make a prediction, let's check out x and y. So right now we have a trained machine learning model. So this is tried to work out the patterns between x and y by doing 5 laps over the data. So let's remind ourselves of what x and y are. There we go. So -7, 3, -4, 6, -1, 9. Now, try and make a prediction using our model. So let's go model.predict. This is how we can make a prediction with our trained model. If we wanted to make a prediction on x equal to 17. So if we had another value on the end here, right, if we added x equals 17 to the end here, what do you think the output should be for y? If you guessed 27, you'd be correct, because that's the pattern between our x and y, is that y equals x plus 10. So let's see what our model learned. Our model predicts that if we had an x value of 17, the y value should be 12.7. Now, that's pretty far off, but as we can see from our loss and MAE values, that actually reflects what our model's training output has shown us here, is that on average, our model predicts something that is basically 11 points off where it should be. So if we wanted to, let's go ypred equals model.predict, have a look at ypred. So this is on average 11 points off where it should be. Ypred plus 11, because I'm getting this value here. What does that give us? 23.7, so it's still off. So, we fit a model. Now, it doesn't find the correct patterns between x and y. So what we might look at doing in the next video is seeing how we can improving our model. So let's check out that in the next video. We finished up the last video with you writing your first neural network with TensorFlow code. Specifically, we stepped through the steps in modeling with TensorFlow. We created a model, we compiled it, and we fit the model to our data. However, our neural network didn't turn out very well. I mean, we tried to make a prediction on a new piece of X data, and the output was pretty far off where it's supposed to be. You might be thinking, hey Daniel, we kind of stepped through this code relatively quickly without discussing the concepts behind it, and you'd be 100% right with that, but there's a reason for it. If we come to our keynote, we checked out this slide, Steps of Modeling with TensorFlow. We had a brief look at our workflow, what we're sort of working on throughout this course. We had an even briefer look at the steps in creating a model, compiling a model, and fitting a model, and then, of course, evaluating it. Well, we do have a bit more of an in-depth guide as to the steps in TensorFlow modeling, more specifically talking through the code we wrote. Now, this is an important point I want to emphasize, and it's going to be a theme throughout the rest of the course, is that I would rather you learn the concepts by writing code than by looking and reading a slide. So I'll say that again. I would much rather, I held this slide back because I would much rather you write code than spend time reading slides. So if we got the steps here, number 1, construct or import a pre-trained model relevant to your problem, compile the model. In the compilation, we define the loss, we define the optimizer, we define the metrics. Number 3, we fit the model to the training data so that it can discover patterns. Epochs is how many times the model will look at the training examples. And number 4 is evaluate the model on the test data. Now, these steps don't necessarily come in this order all the time, but generally, you can adapt them to whatever problem you're working on. So with that being said, we've built our first neural network with TensorFlow, but it didn't perform very well. Let's have a look at how we might improve our model. So I want you to take a guess. We've got 3 steps. We're creating the model, compiling it, and fitting it. Based on what you've seen so far throughout the course, what do you think are some steps that we could do to improve our model's performance? Now, if you're not sure, that is completely fine. I just want you to have a think about it before we start going through it. Remember how we define a model? It's got a number of different hidden layers. It's got a number of different hidden neurons in each of those layers. And we fit it for 5 epochs, which means it looks at the data 5 times. So they're just a few little hints, but let's get on to here. If we wanted to improve our model, let's take a look at the 3 steps we used before to create a model. I want you to think about this, is that when we create a model using these 3 steps, we can actually improve a model by altering how we went through each of these. So when we create a model, we can improve it via steps in the creation. When we compile a model, we can improve it by steps in the compiling. And when we fit a model, we can improve the model by steps in the fit method. So let's write that down. We come here, we can improve our model by altering the steps we took to create a model. So number 1 is creating a model. If we wanted to improve our model here we might add more layers, increase the number of hidden units, also called neurons, within each of those layers, within each of the hidden layers. And we might change the activation functions of each layer. Number 2, when we're compiling a model, here we might, ear. I've written ear up here. Ear, we might. Here, we might change the optimization function, or perhaps the learning rate. We haven't looked at this parameter yet, or hyperparameter, should I say, but we will in a second. Learning rate of said optimization function. And number 3, when we're fitting a model, here we might fit a model for more epochs. In other words, let our model look at the training data more times. So leave it training for longer, or on more data. So give the model more examples to learn from. Now, this is a very brief overview of how we might improve our model. We do have a dedicated slide for looking at this. So improving a model from our model's perspective, that is. So we might start with a smaller model, and then we might build it into a larger model. Now, before we continue with this, we've discussed the concepts of improving our model. Now, what I would rather do, instead of going through each of these one by one, is let's start to code this larger model. So we'll do that in the next video. I'll see you there. Welcome back. We finished the last video by looking at this slide here, comparing our smaller model to a larger model. Now, there's a few key differences between these two. You'll notice in step 1, here the larger model has 3 hidden layers, well, a total of 4 layers, but we've added 3 layers here to the beginning. Whereas this one only has 1 layer. This larger model has 4 layers, so we've increased the number of hidden layers. The number of hidden units, or the neurons, in each of the hidden layers is 100, whereas this one only has 1 hidden layer with 1 hidden neuron. And then if we come down here to step 2, compile the model, let's have a look. What's the main difference here? The main difference, the loss is the same, but we've changed the optimization function from SGD to Atom. So if you're not sure what the Atom optimizer is, just for now, remember, the optimizer tells our model how it can improve. And the Atom optimizer is a very common and very useful optimizer. So this will often be the default optimizer that you start with. We've also got a LR parameter here in our optimizer where this one doesn't have it. So LR is short for learning rate. In other words, when our Atom optimizer tells our model how to improve, how much should it improve each step? So the higher the learning rate, the more the Atom optimizer pushes the model to improve. Whereas the lower the learning rate, so say for example, if we had more zeros here, the lower the learning rate, the smaller the steps our optimizer tells our neural network to take to improve. And now finally, in fit the model, we see here, we've got fit X-train subset, Y-train subset, whereas here we've got X-train full, Y-train full, and epochs equals 100 versus epochs equals 5. So what you'll often do with your data sets is split them into a subset, say for example, 10% of your training data, rather than the full data set. So you can run many smaller models to make sure that they work before upgrading to a larger model. Because this larger model here may take more time to run or time to figure out patterns in the data set than our smaller model. And what do we want to do as data analysts and machine learning engineers is we want to run as many experiments as possible to figure out what doesn't work before we increase the parameters of our experiments and try run some larger models. So let's see. We're going to do it one step at a time. Let's recreate this larger model. But as I said, we won't change every single thing. We won't change the number of layers to begin with. We won't change the optimizer. Let's just see if we can improve it by increasing the number of epochs. So this is a very similar model to what we've built. Let's do one upgrade to it by letting it look at the training data. Rather than 5 times, let's let it look at the training data 100 times. So if we come back, so let's rebuild our model. So number 1 is create the model. Again, you could scroll up if you wanted to, but I'm just going to recreate the same model we created before, tf.keras.sequential. And if you can't remember each of the 3 steps, so create the model, compile the model, fit the model, don't worry, because this may be the first time, or very likely is the first time you've ever written this code. However, by the end of the course, after you've built, I'm not even sure how many we're going to build, I think it's well over 100. Once you've built 100 plus models, these steps you'll start to be very familiar with. And even now, like I've built probably thousands of these, I still make mistakes and I still get things wrong and have to tweak them. So what we've done is we've created the model, which is just the exact same step we did before. It's a sequential model, meaning it's going to run from bottom to top. So you're going to pass through this one layer. We've defined our loss function as mean absolute error. We've defined our optimizer as stochastic gradient descent. And then here we're going to define our evaluation metric as mean absolute error as well. And now, this time, in step 3, fit the model, we're going to go, this time we'll train for longer. We go model.fit x, y, epochs equals 100. So this is the exact same model as we created before up here. The only difference is here, we've changed epochs from 5 to 100. So remember, the final loss and the final MAE for this after 5 epochs was around about 11. So let's just remember 11. That's the number we're trying to get lower. That's what we're trying to improve by increasing the number of epochs. So let's try run this model. You should be very excited too. Oh, see what I mean? I've written thousands of these, but I still get it wrong. It's optimizers, not optimizer. I missed the S on the end. Run it again. Beautiful, look at that. Oh, nice and quick. How exciting is that? Epoch. So if we come down here, scrolling everywhere, right up to the top. So we see here, we've got epoch 1 out of 100. And then this is where our previous model stopped after 5 epochs. So again, the error is very similar. It's very close to 11. But then watch, as we increase the number of epochs, so 6, 7, 8, 9, 10, that's double. Has the loss gone down? It has. So we're getting closer to 10 after 10 epochs. And now let's keep going down to 50 epochs. Here we go, 50. So about halfway through. Oh, we're almost at 7 loss. Okay, let's keep going. All the way down. And we get to 100. Wow. Okay, so we're just below 7 here. This is amazing. So just by altering one hyperparameter of our model, specifically the number of epochs it's gone through, we've decreased our loss and our MAE, mean absolute error, from around about 11 to around about 7. So let's see what our prediction is going to be. So remind ourselves of the data. So we have X and Y. What did we try to make a prediction on before? We tried to make a prediction if we added another value here, 17, which should come out to be about 27, based on the other values of X and the other values of Y. Let's see if our model's prediction has improved. So we go here, model. If we want to make a prediction, predict, we pass it 17. The predict data has to be in the same format as the training data here, so it's in a float there. And ready? 3, 2, 1. Boom. Oh, yes, look at that. So much closer. 29.73 to what it actually should have been is 27. So much better than before. What did we get before? Let's come up here. We got 12 before. So, which is, it should have been 27. That's about 15 off. So we've reduced our error to be about 3 off. How cool is that? By just tweaking one little parameter of our smaller model and turning it closer towards being a larger model. Now, what if we were to alter another one of our model's parameters? What I'll do, before I do that, before I write the code, I'd like you to give it a try. So you see here, we've got our model code here. I'd like you to rewrite this cell. However, this time, keep the number of epochs at 100. I want you to choose one thing from this larger model slide here. It could be the optimizer to change. You could add in here one hidden layer, or you could add in all 3 to the creating a model step. But I'd like you to try one change. And then in the next video, I'm going to go through one of the changes. I'm not going to let you know which one. But just try one of these for yourself and see if it improves our model's results. Just go through the exact same steps that we've done here, creating a model, compiling the model, fitting the model, except this time, maybe add in a hidden layer here, tf kerers ... I'll let you complete that, or change the optimizer to atom and see what happens. So give that a try, and in the next video, I've got to decide what change I'm going to make, and we'll see if we can improve our prediction even further. Welcome back. In the last video, we saw how we could improve our model's prediction capabilities by just increasing the number of times it looked at the training data. Now, an important point to note here is that although we've seen a couple of ways of how we can improve our model, it's not always the case that any one of these parameters here, or hyperparameters, will result in an improvement. So I also issued you the challenge to see if you could change one of the hyperparameters here in creating the model or compiling the model and fitting it to the data, keeping the number of epochs the same, and seeing what happens. So, depending on what you tried, it might have improved the model, might not have. But let's see if we can make another change to improve our model. So now I'm going to write some code to get even closer towards our smaller model becoming our larger model. My change, I'm going to choose by adding an extra layer here. So rather than 3 layers, I'm going to make the smallest change possible. And this is what I'd like you to think about as well going forward, is that you don't necessarily always have to add 3 hidden layers or add 10 hidden layers. You can just adjust one thing on your model, try it out, and see how it goes. In fact, that's how I would like you to run your experiments, is many, many small changes rather than always doing extremely large changes. Because otherwise, if you do too big of a change, you might not be sure what caused the improvement or non-improvement of your model. So let's go here. Let's try, I'll keep that output there. So this time, create the model, this time with an extra hidden layer with 100 hidden units. So let's go here. Model equals tf.keras.sequential. Open a list. I like to come back right to the start here and tab in tf.keras.layers. Now 100, and the activation on this one is going to be ReLU. We'll have a look at what that is in a later video, but if you want to test yourself at researching, have a go at just searching what is ReLU activation, or however you want to pronounce that. So tf.keras.layers, dense 1, beautiful. Now we're going to, number 2 is compile the model. Whenever you create a model in TensorFlow, you have to compile it. Compile the model, model.compile. The loss is going to be tf.keras losses MAE, and the optimizer is going to be tf.keras optimizers.sgd. Now I just want to show you a little tidbit just to prove that it works, is if you didn't want to write this out, you can change this to be MAE. That should work. Fingers crossed. And then metrics is going to be, metrics has to be within a list as well. Metrics is going to be MAE. Now 3 is going to be fit the model. We've got our data, model.fit, x, y. So the features come first, as you see here, model.fit. This is the doc string. X equals our features, y equals the labels. And then we're going to go epochs equals 100. So the only difference we've made to this model above is we've added this hidden layer here. So that's the one change we've made. So let's see how it goes. Shift and enter. Beautiful. Oh, would you look at that? Right from the start. Remember our first model, after 5 epochs, had an error of about 11? Well, this one's hitting about 10. But then after 10 epochs, it's already just above, it's already below our other model without a hidden layer. So this one finished off with a loss of just around about 7 and an MAE of around about 7 as well. Remember, mean absolute error is about, on average, how wrong are our model's predictions. So if we come down here, what did we finish up with here? Oh my goodness, how cool is that? Our next model, by just tweaking one little thing, by just adding an extra hidden layer here, that's all the change that we made, we've basically cut our MAE and our loss in half. So let's remind ourselves of the data. So we have X, Y. Remember, the little prediction test that we've been trying to make is if we had another X over here, which was 17, just increasing in the same way that these numbers are increasing. Let's see, let's try to make a prediction. So we want model.predict, and we want to make a prediction on number 17 to see what the Y value might have been. Oh, okay. So it should be 27. But now we're seeing it's 31.2. If we come up here, it seems that our previous model did better. It got 29.7, which is closer to the actual value it should be, 27, because y equals x plus 10. I wonder why that is, even though our loss and MAE are lower. What it might be doing is our model is overfitting, meaning it's learning the training data too well. So it's learning the patterns between x and y far too well, so when it sees a new x, it's just relating it back to what it knows. And the error that it's producing during training is not a really valid representation of what it's actually doing. See, the real way we evaluate our machine learning models is not the metrics it gives us from the training data. It's the metrics we get from data it's never seen before. Now, if we come back to our improving a model section, we saw a number of different concepts here, but let's step back through them. And I want to emphasize, as we've seen in practice, not all of them lead to an improvement of our model. And as we'll see going forward, sometimes the metrics you see here during training aren't necessarily representative of what you'll see for data the model hasn't seen before. So we're going to cover that in a little bit, but I just want to go back and step through some of the concepts that we've looked at for improving a deep model. So the first one is adding layers. We just saw that. We added one layer, and we got improved metrics during training. So when I say during training, it's when you call the fit function. However, in practice, trying to predict on a sample our model hadn't seen before, the results weren't as good as when we didn't add an extra layer. Another way to improve a model is to increase the number of hidden units. We also saw that. If we come back to our model here, we could build another one by going 50 instead of 100, and we see how this goes. So we'll train the model. That experiment ran nice and quick. Again, we're getting a fairly low loss and a fairly low mean absolute error, but the real evaluation is on a sample that the model hasn't seen before. And we get an even worse value. So we come back here. Again, this is just a great example of how improving a model, or the steps that we're looking at here, don't always result in an improvement of our model. Another way is to change the activation function, which we've tried here. So by default, if we have a look at our docstring, let's see this in practice. Activation, if we go here, get the docstring, the activation is none by default. So what if we just did that? None. And we run. What do we get here? Okay, so we get a slightly higher loss value than before and a slightly higher MAE, but again, those are just metrics during training. We want to evaluate our model on a sample that it hasn't seen. Oh, we're getting closer. 29.5. That's strange. We've reduced the number of hidden units and taken away an activation function, and we're seeing an improvement. We come here, change the optimization function. So in this example of the larger model, we're using the Atom optimizer rather than SGD. So let's go back to our code. And how about we change this from SGD to Atom, and we run it again. Oh, so we get a slightly higher loss than before compared to using SGD, but let's remind ourselves of the data. The training data we already have labels for. So what if we had a new sample that was 17? We want to figure out its label, make a prediction. 31, okay, so it's worse again. Change the learning rate. All right, so we have Atom and it has a parameter LR. The learning rate is if the optimizer tells our model how it should improve, the learning rate tells it by how much. So Atom's learning rate, by default, Command-Shift-Enter, is 0.001. So how about we increase this? We'll increase it by 10. And for this function here, learning underscore rate can be learning underscore rate, or it can be the abbreviation LR. So let's run this again. Oh, wow. Look at that. Our loss and MAE are barely even 1. So theoretically, this model should be really good. Oh, 26.2. That's our best model so far. Because remember, predicting on 17, the ideal value should be 27. So in our case, adjusting the learning rate of our optimizer has resulted in the best change so far. So that's an important point. I want you to keep these things in your mind as we go through. And again, if you've only just experienced this for the first time, I'll give you a little hint. The learning rate is potentially the most important hyperparameter you can change on all of your neural networks. So just keep that in mind going forward. Don't worry too much about it now, but just if you want to take one note from this slide, just write down the learning rate is the most important hyperparameter of many different neural networks. So let's go here. So fitting on more data. So in this case, we have X-trained subset and X-trained full. Well, in our case, we don't actually have more data than X and Y. So maybe that's our next experiment to try, is creating a larger data set. So for now, we only have 8 samples. So in practice, you'll probably have a lot more samples when you're building your neural networks. Let's come back. We've got one more, is fitting for longer. Now, this is the first one we tried, and it's actually probably one of the most easiest to try because we just adjust this from 5 to 100. So now we've seen a few different ways to improve our models and fit them to the training data. Let's have a look in the next video. We're going to have a look at probably just as important as fitting a model to data is evaluating a model's performance. So we've seen here our test example of trying to make a prediction on a sample the model's never seen before. And we keep getting this different number, but how exactly do we tell how good our model's predictions are, or how good the patterns it's learned or the relationships that it's learned between X and Y? Let's check that out in the next video. In the previous video, we checked out a whole bunch of different ways of how we can improve our model. We even tried a few of them, well, most of them actually. We adjusted the number of hidden layers, we changed the optimizer, we changed the learning rate, and we saw that the learning rate actually had probably the biggest influence on how our model performed. And we changed the number of times our models look at the data by altering the epochs. And in practice, this is actually a fairly common workflow. So let's write this down. In practice, a typical workflow you'll go through when building neural networks is we'll start off with build a model and then fit it, evaluate it, and then tweak a model, fit it, evaluate it, and then tweak a model, fit it, evaluate it. Yeah. And now, looking at this, you might think, well, have we actually done this? And the good news is we have. Well, that's just what we went through in the previous video. We created a model, we compiled it, and then we fit it, and then we had a look at the things that we can tweak in our models. We tried adding a layer, so we tweaked our model, we fit it, and then we evaluated it. We tried increasing the number of hidden units, then we fit it, then we evaluated it. We tried changing the activation function, the optimization function, the learning rate. We didn't try this, fitting on more data, but we're going to see that in this video or maybe the next one. And then we tried fitting for longer by increasing the number of epochs. And because you can alter each of these, they're referred to as hyperparameters. Remember, a hyperparameter is like a dial on your neural network that you can adjust to see how it improves. Whereas a parameter is usually the patterns a neural network learns. So these are the things that we don't code ourselves. So let's go back. Let's see some other ways for evaluating our model. We tried by making a prediction on an example the model hadn't seen before. But what are some other options that we have? Well, when it comes to evaluation, there are 3 words you should memorize. When we're building models, you want to experiment. But when we're evaluating models, it's visualize. So that's the most important step. when we're evaluating our models. Now, what should we visualize? So, it's a good idea. What I mean by visualize, we'll see in a second. Visualize, but you can probably guess. It means when we're looking at things like this, it can be hard to really understand what's going on. But when we put them in a way that we can visually see what's going on, so we might visualize the data. So ask ourselves, what data are we working with? What does it look like? We might also visualize the model itself. What does our model look like? We might visualize the training of a model. So how does a model perform while it learns? And we also might visualize the predictions. We've done this one of the model. How do the predictions of a model line up against the ground truth? The original labels. We tried this one. So this is lining up this prediction here against what it should actually be. So if we try to predict on 17, that's our x value, we know that y equals x plus 10, so it should be 27. Let's really dig into these steps here a bit further by working on a little bit of a larger problem, which is going to suit this step here, so fitting on more data. But first we'll need to make a bigger data set. And we can do that. Let's set up another x. We'll use TF range to create a range of numbers between 100, negative 100, and 100 with a step of 4. Let's see what this looks like. Beautiful. So we have 50 numbers here that start from negative 100 and increase by 4 all the way up to 96 because the maximum was 100. So 50, how many did we have in our previous x? Oh, it's not saved up here. There we go. So 8. So we got 5 times as much data. That's a good amount for now. And to do so, we're going to need to make labels for the data set. So y can just equal x plus 10. This is the formula we want our model to learn. This is a pattern we want our model to learn. Now let's have a look at y, just as before. There we go. Negative 90. Yep, negative 100 plus 10 is negative 90, all the way up to 106. So we had the same shape. So one y value for every x value. Beautiful. And now, what should we do? So it's a good idea to visualize the data. All right. So let's visualize the data. What we might do is create a plot. So import matplotlib.pyplot as PLT. Google Colab completes that for us. So plt.plot x, y. What does this look like? Oh, wonderful. How about we get that in a scatter plot? I think that's a better plot for this type of data. Yep, we should have dots there. Now, before we trained our model on x and y, and then we evaluated it on a sample our model hadn't seen before. Now, this is one of the most important concepts in machine learning and deep learning in general. And it's probably better explained using 3 sets. So before we get into visualizing the data, the model itself, the training of a model, and the predictions of a model, and even further into evaluating our model, let's take a look at the concept of the 3 sets. Now, if you're familiar with machine learning, you may already know what the 3 sets are. And so I would like you to apply your knowledge of the 3 sets. And actually, we're probably only going to use 2 sets. So split x and y into a training and a test set, only if you're familiar with it. If not, just go straight into the next video. If you are familiar with it, split x and y into an 80% training and a 20% test set. We'll see how to do that in the next video. Welcome back. In the last video, we touched upon the concept of the 3 sets. So let's dig into what I mean by that. So go here. Now, in practice, in machine learning, you're often not going to fit and evaluate on the same data set. And what I mean by that is what we did up here. We started with x and y, and we just fit the model to all of the data in one hit. And then we had to evaluate on our own custom sample. Whereas when you actually work on machine learning problems, you're often going to have 3 different sets of data. You're going to have the training set. So the model learns from this data. Now this is typically, depending on what problem you're working on, typically 70 to 80% of the total data you have available. And then we want a validation set. So the model gets tuned on this data. So this is where you would tweak different things. So if we come back up to here and we built a model, we fit it, we evaluated it, then we tweaked it. So say changing the number of hidden layers or changing the optimizer, you'll often test how these tweaks affected your model's performance on the validation set. So this is typically 10 to 15% of the data available. Again, this will generally depend on how much data you have. And then finally, you have the test set. So the model gets evaluated on this data to test what it has learned. This set is typically 10 to 15% of the total data available. So if you had a go at creating your own training and test set, you might have split it. I think I said 80 and 20%. So that's another valid training and test split. If you are going to drop one of these sets, usually you'll get rid of the validation set and you'll only have a training set and a test set. Again, will depend on how much data you have, will depend on the experiments you're running, but we've spent enough time talking about these. Let's get into coding them up. So here, if you want another analogy, we've got the slide here. We have 3 data sets, which is possibly the most important concept in machine learning, is to have the training set, which could be, if you were studying at university, your course materials, so the things you learn throughout the semester. The validation set is the practice exam, and the test set is your final exam to evaluate the knowledge you learned throughout the semester. And what we're going for here with the 3 data sets, the training, validation, and test set, is generalization. So this is the ideal state we want our machine learning model or deep learning model to be in, is the ability for a machine learning model to perform well on data it hasn't seen before. So if you've learned well the course materials throughout the university semester, you should be able to perform well on the final exam. So something you haven't seen before, if you've learned them well. Now, this is exactly what we want for our machine learning models to do, is we want them to learn patterns on the training set so that it can perform well on samples that it has never seen before. In other words, perform well on its final exam. So let's go back. Let's see how we might code these in practice. So check the length of how many samples we have. So len x, this is the data we're working with. We created this just before. By x is TF range, -100 to 100. Wonderful. Now, knowing this, we're going to skip our validation set for now. We'll see it later, but because we only have a relatively small sample, 50 is pretty small in the world of deep learning. What's a large one? Well, again, I would say minimum 100 plus samples for deep learning, but we'll see in future videos different sizes of samples. Now, the training set is typically 70 to 80% of the total data we have available. Why don't we use 80? And that means we're going to create a test set, so in other words, the final exam, of 20% of the total data available. So how might we do that? Well, we can go here, split the data into train and test sets. Xtrain, you'll often see, or this is kind of be the notation for a training data set throughout the course, is just with the train tag after. This is very common in practice. Sometimes you'll see something like train data equals this. They usually just mean similar things, and the same for xtest equals or test data equals. So just going forward, if you see different variable names for training and test data, they're often the same thing. Different ways of representing the same thing. And then we'll go x test. So this will be the training data. So we want the first, because we're working with 50 samples, we want the first 40 training samples. This is 80% of the data. Wonderful. And then X test is going to be the last 10 samples. So last 10 testing samples. 20% of the data. Beautiful. And here we'll create Y train as well, just in the same format. And we'll also create Y train here. Oh, we've got a space there. Oh, we've got a space there too. Y40. Wonderful. And we can have a look at length of X train and len X test. So this should be 40 and 10 respectively. Beautiful. So what we've done is we've created a training data set and a test data set. We've also got Y train, which are the training labels, and Y test, which are the test labels. Y test is not defined. There we go. See? We're catching errors together. Beautiful. So we've got training features, testing features, training labels, testing labels. Now, what should we do? How about we go back to what our steps are in evaluating? So when it comes to evaluating, we should remember 3 words. Visualize, visualize, visualize. Wonderful. That's our data evaluation motto. It's a good idea to visualize the data. All right. Well, we did that before we split our data into training and test. But now let's visualize our data split into training and test samples. So how about we go here, visualizing the data. And we'll go, now we've got our data in training and test sets. Let's visualize it again. Now, if you're wondering what I'm putting here, when I write text in Colab notebooks or in Jupyter notebooks, depending on what you're using, I often write like text cells. These are just kind of notes to myself. Or if I had to share this notebook with someone else, it's information so they know what's going on, kind of like a comment, but just in a text format that's easier to understand. So that was a little bit of an aside. Let's write some code. So we want to set up a matplotlib figure because this time we're going to be plotting 2 samples of data, our training and test. So 10.7 is my favorite plot size. So plot training data in, what's a good color? Blue. Plot scatter. We're going to go X train first. So we need to plot X train and Y train. We can use the C parameter of plot to set as B for blue. And then we're going to label it with training data. Wonderful. And now we're going to plot test data in my favorite color, green. Plot scatter, X test, Y test. We're going to set the color to G for green. And we'll set a label as testing data. Beautiful. And we want to show a legend so we can tell the different data apart. And we'll put this little semicolon at the end so we don't get the matplotlib output. Shift and enter. What does this look like? Ho-ho! There we go. We've got a very similar plot to just above. So this one here. Except now we have our testing data, training data in blue, and our testing data in green. So anytime you can visualize your data, your model, your anything, it's a good idea. So that way it's much easier to understand. Well, in my case, I find looking at something like this much easier to understand than looking at something like this. All these numbers in a tensor. So in some cases, you won't be able to plot your data if you've got more dimensions than just X and Y. Sorry, X there, Y there. Now, what are we going to do? Referring back to our concept of 3 data sets, in our case, we haven't got a validation set. We've got a training set, which is the blue, and the test set, which is the green. So what we want to do is build a neural network to take in the training data here, to learn the relationship between X and Y, And then if we want to feed in, we want our model to learn the relationship in the training data so that it can predict our test data. So if we fed it in the X values of our test data, we want our model to be able to predict the Y values, so where this green line should be. So now we've visualized our data in our training and test sets, let's build a model in the next video to figure out the patterns in the training data so we can make predictions on the testing data. Welcome back. In the last video, we split our data into training and test sets. And then we had a go at, did I spell that right? Nope, again, another spelling mistake. Plenty of them throughout the course. We had a go at visualizing our data, more specifically comparing our training data to the testing data. And we want our model to learn on the training data, and we want our model to be able to predict the testing data. In other words, given X, what's the Y value? So let's have a look at how to build a neural network for our data. Now, we've actually already done this. So if we scroll back up, we built a neural network very similar to what we need right up here. So let's recreate something like this. Nice and simple neural network, one layer, and we'll create it, compile it, and fit it. We'll come back down. Beautiful. So step one, I told you we're going to get lots of practice creating a model. Create a model. So model equals TF Keras sequential. And then we'll put in one layer, TF Keras layers, dense, one hidden unit, because remember, where our X and Y vectors, or tensors, we're using one X value to predict one Y value, hence why our dense layer has one hidden unit. Two, we're going to compile the model. Model.compile. We need to set a loss function, TF Keras losses.mae. We're going to set an optimizer, which is telling our model how it should improve. Optimizers, SGD, stochastic gradient descent. And we're going to set the metrics to be MAE. Wonderful. Number 3 is fit the model. I'm going to do model.fit on xtrain. This time is different. We want to fit on the training data only for, let's go 100 epochs. So notice here, the important point, we're fitting on the training data, which is this blue line here. So we want our model to learn the patterns in this training data to be able to predict the patterns in the test data. So before we fit the model, I'm going to comment out this line. And I'm going to hit Shift and Enter. I'm going to instantiate our model here. Now, because what I want us to have a look at is visualizing the model. So we can get an idea of what our model looks like before we've even run it by running model.summary. Oh, what happened here? A value error. This model has not yet been built. Oh, why is that? Build the model first by calling build or calling fit with some data, or specify an input shape argument in the first layers for an automatic build. Now, you might see why I commented out this line. I did this on purpose because I wanted you to see this error. So build the model first by calling .build. So we could go model.build, and we see what that might do. So builds the model based on input shapes received. We could define the input shape there. So that's one option. That's the first one. You could try that out for yourself. Or we could specify an input shape argument in the first layers for an automatic build. So with that in mind, let's see how let's create a model which builds automatically by defining the input shape argument in the first layer. Let's see what that might look like, because this is something you'll do quite often in practice, is defining the input shape. Usually your neural networks can determine the input shape. So this is what I mean by input shape, is this parameter here, input shape. Usually they can figure it out, the input shape, on their own. However, sometimes you'll need to manually define it, depending on what problem you're working on. So let's see how we might do that. So we'll set the random seed. So TF random set seed for as much reproducibility as we can. So we'll create a model. This is just the same as above. And we're going to go model equals TF Keras sequential. Remember, a sequential model just runs from top to bottom. We're going to go TF Keras layers dense 1. Now here's what we're going to do. The input shape argument, we need to define that. So how might we find the input shape? Remember, what are we trying to do? We're trying to predict y based on x. So what is the shape of the data that we're passing our model? X.shape. 50, but we want just one sample of x.shape. It's a scalar value. So what if we do, what is x0 and y0? What do they look like again? They're just one number. So in our case, the input shape will be 1, because we're passing it one number to predict one number. So there we go. We've specified the input shape argument. Now, again, the shape might be different depending on the input tensor you're passing in. You might have 3 different variables. So you could pass the input shape as 3. But for our case, we have one input for one output. That's what we're after. Now, we might go, number 2 is compile the model. Model.compile loss equals TF Keras losses MAE optimizer equals TF Keras optimizers dot SGD stochastic gradient descent metrics equals mean absolute error. So if we run this, just the same model we've created before. This is also the same as above. Now let's check out our model.summary. Whoa. Okay, we've got a few things going on here. So calling .summary on our model shows us the layers that it contains, the output shape, and the number of parameters of each layer. So the output shape here is, remember, we want one input for one output. So the output of 1, that makes sense. The layer here is a type dense. So another word for dense is fully connected. So if we go here, fully connected layer, images, what this means in a fully connected layer is that all of the neurons here connected to all of the neurons in the next layer. So that's what fully connected means. And in TensorFlow, a fully connected layer, when you see that, is the same as a dense layer. So dense is just another word for dense connections, if you see all those connections there. And then we've got parameter numbers here. Now, there's a few different things here. We've got total params, trainable params, non-trainable params. So let's define what each of these are. So the total params is total number, as you might have guessed, of parameters in the model. These are the patterns that the model is going to learn. So remember when we had a look at our overview of a neural network, it creates tensors of different values, so patterns. The total number of parameters are how many different patterns our model is going to try and learn within the relationship between, where's our X and Y data? Here, the relationship between our X and Y data. So we come down, and the trainable parameters, these are the parameters, the patterns, the model can update as it trains. So in our case, the total number of parameters here, 2, is equal to the trainable parameters. That means all the parameters in the model are trainable, so they can be updated. You might be wondering, when is ever total params different to trainable params and different to non-trainable params? Well, when we later on in the course, when we import a model that has already learned patterns in data, what we might do is freeze those learned patterns. So in that case, it might have a whole bunch of non-trainable parameters because we want that model that has already learned on data to keep its existing patterns. We just want to train a few parameters and apply it to our own problem. So let's write this down. Non-trainable params. So these parameters aren't updated during training. This is typical, as we discussed, when you bring in already learned patterns or parameters from other models during transfer learning. We haven't covered transfer learning yet, but we will in a future video. So this is a little bit of an overview of what you get of calling .summary. Now, if you want to have a look at what the actual parameters are in a dense layer, you're going to probably find something called a weights matrix and a bias vector. So if we go here, neural network, weights, and biases. Here we go. Fundamentals of neural networks on weights and biases. So if we look at this, basic neural network structure. So within our hidden layer, here, we've got hidden layer 1, hidden layer 2, hidden layer 3. We have a whole bunch of different parameters. Where's the weights and biases metric? There's a lot of good stuff going on here. Weights and biases. This is the type of research that you're going to have to do. Maybe that's not the best article, but Weights and Biases is a great website. Here we go, neural networks, biases, and weights. We'll try another one. Or, I got a better question. So, here's an example of how to do better research. Is what were we actually looking for? Now, I gave away there that it's a weights matrix and a bias vector. But what were we actually looking for to begin with? We don't know what the trainable params are. So if we search, what are the trainable params in a neural network? Learnable parameters. Here we go. Trainable params. Much better question. So if we come back here, this is an example of how to rephrase what you're looking for to find out in a better way. So if we come here, learnable parameters, Keras, Python deep learning, trainable params. There's a video there. Have we got here? Model.summary. There we go. Trainable params. This model has far more, 2,515. There we go. If you recall from that episode in our first convolutional layer, we haven't looked at convolutional layers yet, giving us a total of 2,515 learnable parameters. I'll leave you to do some more research here, but that's a great way to phrase a question. I have an external resource for you here while we're at it. So this is one of my favorites. We'll create the resource emoji. Resource. If you want to learn what the actual parameters are here that's going on, remember, we're focused on writing this code. If you want to learn what's going on in the background, I recommend this resource. One, you could ask a question like this to Google, or you could go to this resource for a more in-depth overview of the trainable parameters within a layer. So this will be one of the extra curriculum for this section. Check out MIT's Introduction to Deep Learning video. So we go MIT Introduction to Deep Learning. And there's a full-blown course. Here we go. Introduction to Deep Learning. Intro to deeplearning.com. I'll leave this video, by the way, in the resources section. So Intro to Deep Learning. Oh, they might be uploading it. Oh, it's a 2021. Look at that. So this is the video I'm talking about. By the time you watch this course, they may have the 2021 version. I will share the most relevant one to the course. So this is Intro to Deep Learning. If you want to learn what's going on behind the code, so the trainable params here, you can find out in that video. Otherwise, I got an exercise for you before the next video. In this course, dancing emoji. You can dance if you want, but here's your exercise. Exercise. So try playing around with the number of hidden units in the dense layer, and then see how that affects the number of parameters, total and trainable, by calling model.summary. I'll give you a demo. So if we were to change this from 1 to 3, shift and enter, and then hit model summary, look what changes, 3. So that gives me an inkling that there's 2 trainable parameters per hidden unit. That's all I'm going to let you know for now, because I want you to have a go at going through an external resource as well as adjusting the hidden units on your own and seeing what comes out. For now, all you need to do is think about these parameters as they are learnable patterns in the data we're working with. So with that being said, let's fit our model to the training data. Let's fit our model to the training data. We can do this by going model.fit. We commented this out before, actually. So just the exact same thing here. We can call that here xtrain, ytrain. Epochs equals 100. And I'm going to set a little parameter here called verbose equals 0. Remember, how can we check what that does? Verbose equals 1 by default. What does verbose do here? What does it say? Epochs verbose. 0, 1, or 2 for verbosity mode. 0 equals silent, so that means there will be no output. Progress bar, 1, that's default. Note that the progress bar is not particularly useful when logged to a file. So verbose equals 2 is recommended when not running interactively. So verbose equals 0. Oh, what happened there? We didn't even get any outputs. Because we set verbose to 0. If we set it to 1, we can watch our model train. Look at that! We'll set it back to 0. Now remember, because we're running this continually, every time we call fit, it's going to fit for an extra 100 epochs. So we've actually just fit our model for 200 total epochs. Now if we call that again, that's 300 total epochs because we've called 100 3 times. To reset that, we'd have to go up here, reinstantiate our model, get the summary. I might change this back to 1. Model.summary. And then we're going to fit it. And then we're going to leave it at that. And we'll continue on in the next video. Welcome back. We finished the last video by fitting our model to the training data for 100 epochs. We set verbose equal to 0 so we don't get any output. Now, I did also set a little exercise here. Try playing around with the number of hidden units in the dense layer and see how that affects the number of parameters, total and trainable, by calling model.summary. So let's try that out. If we call, or we'll just get a summary of our model. So model.summary. Okay, and notice this number here continually increases because we've created a total of 14 sequential models so far, at least in this Colab instance. So as I said before, when you first start writing models, you may not get familiar. By the time this number approaches 100 plus, we've created 100 plus sequential models, maybe we'll be pretty familiar with what's going on. And we had a look at the total params, trainable params, and non-trainable params, which are the patterns in our neural network, and the parameter numbers here per layer. And if you wanted to learn a little bit more about what they actually are, we've got this extracurricular resource here, so MIT's Introduction to Deep Learning video. Now, let's do a little exercise. If we were to change this to 10, we'll get model summary. Okay, number of parameters equals to 20. If we fit our model, takes almost no time at all, wonderful. We get a summary of our model. Notice here that sequential went from 14 to 15 and dense went from 19 to 20 because we instantiated a new model here. And then we've got a different output shape and a different number of parameters. So because we've got 10 hidden units in our dense layer, there seems to be 2 trainable parameters per dense hidden unit. Now, there's one more way we can visualize our model, and that's using the plot model function from Keras utility, utils, or from tensorflow.keras.utils. Let's import plot model, and then we can go plot model, and we'll check the doc string here. Is it going to come up? We'll just error it out. So sometimes when you write an import statement and the function hasn't quite been import yet, checking out the doc string by pressing Command-Shift-Enter or Control-Shift-Enter on Windows might not come up until you've actually imported that function. So that's why I just ran it. It's not going to run anything. It's going to error out because it's missing one required positional argument, but that's all right because we can check it here. Convert to Keras model to dot format and save to a file. Okay. What's the example? tf.keras.utils.plotModel model. Let's have a look at what it looks like. Model equals model. Ah, okay. So we've got an input layer. It's going to pass that to our dense layer. All right. So if we go show shapes. So if we look at what this parameter does, def plot model, model to file. If we wanted to save this as an image, we can plot it to, we can set the to file parameter. But if we want to see the shapes of our model, show shapes is by default set to false. So we want this to be true. Remember, a lot of the time we'll spend with our neural networks making sure our input and output shapes are correct. So in our case, we have a dense input layer with an input of 1 and a dense output layer with an output of 10. Although this type of model here is relatively simple, this plot model function is going to be very handy later on when we start to create more complex models with more hidden layers. So we see here, we've defined the input shape as 1. So that's why we have an input shape as 1. And our output shape is 10 because we have 10 hidden units in our dense layer. Now, how might this change if we created tf.keras.layers.dense 1. And I'm going to name it output layer. And this can be name equals input layer. And I'm going to name the whole model as name one of many models we're going to build. All right, model.summary. Now, notice how this changed. Model is one of many models we're going to build. Of course, you can name it something more specific to your problem, but you also see how we've changed the layer names. So before that was like dense 20 or something like that. We've now got a layer with the input layer name, and we've now got a layer with the output layer name. Now, this is very helpful if you have models with, say, 20 or even 5 layers. It's confusing if you're not sure which layer is which. So then we fit our model. One of many layers we're going to build. Oh, the value error. So we can't actually call our model that. So that's an invalid name. So let's just call it model 1. Model summary. Fit the model. That worked. Wonderful. Model summary again. There we go. Model 1. Layer, input layer, layer, output layer. And let's see how this updates. Plot model. Beautiful. That makes a lot more sense. So the input layer input is 1. Then we've got an input layer with a hidden size of 10. Then we've got an output layer of 1. So the input this layer takes is 10, and the output it gives is 1. Now, again, looking at this might seem quite confusing, but as I said, as we go on, as we start to build more models, as we start to visualize them, it's going to start to make more sense. So with that being said, let's stick with our theme of visualize, visualize, visualize. And in the next video, let's check out how we might visualizing our models' predictions. So have a go at creating your own different models. Maybe add some hidden layers here, give them different names, change the number of hidden units you have here, and then fit it to the data, get a summary, see how high you can get this number of trainable parameters, and then plot the model here using the plot model utility. And I'll see you in the next video. In the last video, we saw how we could visualize the different layers